Hello, hello, hello. Today I will discuss with you the solutions to the Birefringence problem. Very difficult subject that most of you have never even heard of. Normally my solutions last maybe 10 minutes, sometimes a little longer. This time they may last almost 45 minutes. This time it's a mini lecture. I've worked very hard on that lecture. And at the very end I do two demonstrations. Now, if you don't have the time to watch the solutions, or if you couldn't care less about Birefringence, that's okay with me. Of course we'll be friends. And if you only want to see the demonstrations, go to the very end and look at the demonstrations. However, if you only look at the demonstrations, you won't learn much, because you have no idea why you see what you see. All right? You make up your mind, and whatever you want to do, we will be friends anyhow. If you're ready, I'm ready. Hello, hello, hello. Solution to the difficult chord problem which deals with Birefringence. Try to follow me step by step. There are crystals, mica, calcite, quartz, and there are many others, which are anisotropic. They have optically anisotropic features, which would mean that different directions of polarization may propagate through that medium with different speeds. And that idea is called Birefringence. Let this be one of such crystals, and we identify an optical axis. I've assumed it to be in this direction. Of course, it's everywhere in this direction. This is one crystal. And I have polarized light falling perpendicular on this, and the plane of incidence is the plane through the light and the optical axis. That's the way I arrange it. I've polarized this light, linearly polarized, and as it enters this crystal, the polarization breaks up in two directions. One which is in the plane of incidence, and the other one is perpendicular to the plane of incidence. The one in the plane of incidence is called the extraordinary wave, and the one perpendicular to that is called the ordinary wave. O stands for ordinary, E stands for extraordinary. And they propagate, the O and the E waves propagate with different speeds. They have different indices of refraction. The speed, which is the O wave, the ordinary wave propagates, is C over NO, which is larger than VE is C over NE. In the case of quartz, it is larger. That's why I put already a larger sign here. I was a little bit ahead of myself. You will see that shortly. I have here Ne and N0 for quartz and for calcite. I will work mostly with quartz, and you will see that NO is smaller than Ne. So that means this speed is larger than that speed, because NO is smaller than Ne. And the wavelength in that medium of the extraordinary wave is the wavelengths in air divided by NE, and the wavelengths for ordinary wave is lambda air divided by NO. And in our case, lambda O is larger than lambda E. The frequencies, of course, of the two are the same. Let's keep in mind, for instance, that we have chromochromatic, green light, 500 nanometers, and so the frequency of this component and this component are the same. Now, since these two waves propagate with different speeds, when they have traveled through a distance d, there is a phase difference between those two components. And it shouldn't be too difficult for you to show that if the thickness of the plate is d, then the phase difference between the two waves is 2 pi d times NE minus N0 divided by lambda r, by lambda air, the wavelength in air. Suppose d was the same thickness as lambda air. This is about, for quartz, this is about 1/100th. So then, the phase difference would be about 1/100th of 2 pi. Today, we're going to be interested in not 1/100th of 2 pi, but pi over 2. We're interested today in a 90-degree phase difference. So we are going to make the thickness of the plate of the birefringence material such that the phase difference between the two waves is pi over 2, and we call therefore the thickness a quarter wave plate. That's the name. So we make delta pi over 2, and you find then immediately that in the case of quartz that the thickness of that birefringence material, that quartz, would have to be a little less than 14 microns. Way thicker than one wavelength. So the name a quarter wavelength plate is a little bit misleading because it's not, the thickness is not a quarter of the wavelength. Okay? It is the phase difference that is 90 degrees. That's why the word a quarter comes in. 1/4 of 360 degrees. Now comes something that is very important for our problem. Depending upon the direction of the linear polarization that comes in, what comes out is always, with a quarter wave plate, that the phase difference between the two is 90 degrees. But one component could be way larger than the other. Suppose the linear polarized light that you shine in, suppose it is in this direction, then there is not even any O component, there is only an E component. Or suppose you were shining it in this direction, well then there would only be an O component and no E component. However, in our case, and that is built in that secret little plate, in our case we make the E component the same strength as the O component. And that's easy done. If this is the optical axis, and if the light that we shine in is linearly polarized in this direction, an angle of 45 degrees, then the O component has the same strength, the same maximum E vector as the E component. And that's small little plate of ours that I showed you is really a combination between two plates which are glued on top of each other. One is a linear polarizer that does it, that makes sure that the E and the O component is the same, and the second one is the quartz. And so the way that these two are arranged, that either the quartz optical axis is rotated 45 degrees relative to the linear polarizer, or the linear polarizer is rotated 45 degrees relative to the optical axis. Of course, that's the same thing. So now, what we have created is circular polarized light. Because now we have changed the phase by 90 degrees between these two components. And that means, and that shouldn't take you very long, to see that now the E vector will be rotating like this, going around in a circle like this. When this one is here, the O component is faster, the O component is here. Right? It's the fastest one. It's ahead in phase. So the E vector is here. When the E vector is here, the O vector is there. And so you see that you now have linear, circularly polarized light going in this direction. Give this a little bit of time and let this sink in. I will now stop this for a few minutes and I will replace my battery. So key is that you have linearly polarized light, polarized in the direction which is 40 degrees different from the optical axis, so that the extraordinary and the ordinary component have the same strength. I then move it through a quarter wave plate, in this case quartz, and what comes out, and that means what hits the coin, is now circularly polarized light, polarized in our case in this direction. Okay. So I will interrupt this. All right, I'm back on the air. I have replaced my battery. So now we have circularly polarized light, which is produced by a linear polarizer and by the Birefringence quarter wave plate, and the coin is behind it. So the circularly polarized light, which is in this direction, you can derive that from here, because of the 90 degree phase difference, this now hits the metal coin. And when electromagnetic waves reflect off metal, the direction of the E vectors flip over 180 degrees. That's a separate issue, but quite easy to understand why that is. So as a result of that, if this is the circular polarization that comes into the coin, when I look at the coin, when I look in the direction of the coin, the circular polarized light that comes back at me, that comes back right from the metal, is in this direction. Many of you think now that this circular polarized light and this circular polarized light interfere with each other and that the net result is zero. It's very clever, but it's totally wrong. Because the only light that you will see when you look at this side is, of course, the light that comes back at you. That's this light. Now, of course, it has to go through the quarter wave plate, and then it has to go through the linear polarizer, and then it comes into my eye. And now comes the remarkable thing. The easiest way to see what I'm going to tell you is the following. Put yourself at the location of the metal. And so look at me. Then the circular polarized light is circulating in this direction. When it comes to me, from my point of view, looking at the coin, it is like this. But from the coin's point of view, looking at me, it is again like this. And so, what happens now inside the quartz plate is there is again an additional 90-degree phase difference over and above the first one. And that has immensely interesting consequences. I leave you with this. So I will leave you with the idea that if this light has to go through the quartz plate, that means the quartz plate is again a quarter wave plate for that radiation. And that radiation, which was circular, will now become again linearly polarized, but not in the original direction. It has flipped 90 degrees. And so I leave you with that, because that is really not a very difficult exercise. So what went in like this now comes out like this. It comes out of the quarter plate in my direction. But now it has to go through the linear polarizer. And the linear polarizer says, sorry, any light that is linearly polarized in this direction I will block. So this light that now comes back at me is blocked and the coin is black. So the remarkable thing is, you first create circular polarized radiation. First it goes through a linear polarizer, then it goes through a quarter wave plate. The angle between the optical axis and the linear polarization is 45 degrees. It refracts off the metal. It changes direction of rotation from your point of view, but not from the point of view of the metal. The metal will see it going through in the same direction that you would see it go to the metal. Okay, so in any case, the linear polarization flips over by 90 degrees, and therefore it's blocked completely and the coin is black. Now, what I leave you with also, now we flip this over. We put the quarter wave plate first, then the linear polarizer, and then the coin. Go through it for yourself. You don't even create circular polarization when it goes onto the coin. All you create when you go into the coin, it first goes through the quarter wave plate, so the radiation goes through the quarter wave plate. Then it all is going to be coming linearly polarized in a particular direction. Then it reflects, and then that linearly polarized light goes through the quartz plate. And so it might actually become, again, circularly polarized light. Because you have linearly polarized light which goes now into the quartz plate, into my eyes, so it's probably again circularly polarized. So it's not black. So the whole idea is when you flip this over and you look at the coin is visible. But you may have to do some work for yourself. There is one catch. And the catch is that the thickness, the quarter wave plate thickness that we calculated, we used for lambda green light, 500 nanometers. But if my light source has also blue light and red light, then the thickness for it to be quarter wave plate would be 11.1 microns for the 400 nanometers and 16.7 for the 600 nanometers. Because look, it's linearly proportional to lambda of air. So the net result is that it's only perfect for the green light, not so perfect for the blue and for the red light. It never becomes perfectly circularly polarized when it reaches the metal coin. So it's probably going to be elliptically polarized, something like this. And so when it finally hits the linear polarizer when it comes out, maybe only 80% of it will be killed, but certainly not 100%. So when we say the coin is black, yeah, very close to black, but not exactly black. But the light that I was using, which is the light in my room, has its maximum intensity in the green area and not in the blue and the red. So really it looks as black as I can get it. But it is not really exactly black. So the light entering the metal and then coming back from the metal went twice through a quarter wave plate. That is equivalent to going once through a half wave plate. I happen to have a half wave plate. And my half wave plate is of course twice this. So it's a single half wave plate, no polarizer attached to it. And I'm going to show you in front of my computer the following demonstration, which is interesting. If two quarter wave plates can rotate linear polarized light by 90 degrees, because that's what happened, right? That's why you see black light, no light at all, because it cannot go through the first linear polarizer, because it was rotated by 90 degrees. Therefore, a half wave plate should also be able to rotate linear polarized light by 90 degrees if you do all the right tricks and make the optical axis at an angle of 45 degrees with the direction of polarization. And I'm going to do that in front of my computer. I will have two linear polarizers, both in the same direction polarized. And light falls in from behind. So this one polarizes it like this, and this one lets the light through because they are polarized in the same direction. Now I put my half wave plate in between the two, and I rotate it so that I hit the 45-degree angle. The linear polarized light will now be rotated by 90 degrees by this Birefringent quartz material. And so this one will block it completely. So without the Birefringence in between, the light will fall through nicely. The moment I put in the Birefringent material in between and rotate it at the right angle, you will see at the right angle, you will see that no light anymore will come through this, because that linearly polarized light coming in this direction is now converted to this direction, and so this will block it. I will do a second demo in front of my computer. Plastic, any plastic that you have, transparent plastic, is Birefringent. And that means the degree of birefringence is the result of stress in the plastic. And that occurs when the plastic is being made. But the stress is very different at different locations. So the optical axes are all in wild directions. If, however, I shine linearly polarized light through the birefringent plastic, and I look at the birefringent plastic through my own linear polarizer, I will see the most amazing colorful things. Some of that light that comes out of the plastic may be circularly polarized, some of it may be linearly polarized, some of it may have rotated 90 degrees. It's all over the place different because of the optical axes are different. And so I will see the most spectacular colors, and I will show you that when I move the linear polarizer in my hand around and I rotate it. So that will be the end of my solutions. Alright, this was not easy, and I never said it was easy, and it is certainly not high school physics. I hope you will still want to be friends with me. Have a nice day and take care. Once more, hello. I was thinking last night, it kept me awake, that for those of you who are not familiar with circular polarized light, I didn't tell them what it really looks like. I just drew a circle with an arrow in it. So I do want to explain that in a little bit more detail. So the extraordinary and the ordinary wave, of course, have the same frequency. The frequency is set by the fact that we have 500 nanometers light, monochromatic light. And so, since the wavelength in air is the speed of light divided by the frequency, and throughout this whole experiment, frequency never changes. When the light gets into the polarizer or it gets into the birefringence material, wavelengths may change, but frequencies don't. So the frequency is then about 6.00 times 10 to the 14th. I mentioned approximately because I took for C 3 times 10 to the 8 meters per second, and it is not exactly 3 times 10 to the 8 meters per second. So, if this is the piece of birefringent material, the thickness, so the thickness is 13.9 microns, remember? That means that since the O wave travels faster than the E wave, that when the E wave is here, the O wave is there. And you can calculate that this difference is about 8 times 10 to the minus 8 meters. And that is about 1/4 of the wavelength of the O wave, which is about the same as the wavelength of the E wave, of course. They only differ by 0.58%. So, what it comes down to is that as the light travels through the 13.9 microns, that the E wave oscillates 25 times, but the O wave oscillates 24.75. And that gives it the difference of 1/4 wavelength, and that translates into a phase difference of 90 degrees. Now, I will try to zero in a little bit on this. Linearly polarized light, the E vectors go like this, or like this, or like this, and like this, if they are linearly polarized. Circular polarized light, the E vector does this. It goes around like this. As opposed to linearly polarized light like this. Let me try to make you see. Okay. So I hope you can see this. It's not the best quality. So there is a linear polarizer on the left which creates linearly polarized light. It's tilted at an angle of 45 degrees. And so it's linearly polarized like this. Then it hits the quarter wave plate, maybe you can read that, quarter wave plate, which in our case has just the right thickness for, in our case for quartz, 13.9 microns. And then out of this birefringent material comes the circular polarized light. Forget the word left-handed, because we never discussed left-handed and right-handed. It's circularly polarized light. And so with some imagination you can just see that the E vector is going around like this as it propagates out. So maybe this helps you, for those who do not know what circularly polarized light is. So now, if you get ready for my two demos. One demo I will demonstrate that with a half wave plate, and I have a whole set of wave plates, believe me, I have quarter wave plates and half wave plates, that with a half wave plate I can rotate linearly polarized light the direction by 90 degrees. And then, to put some icing on the cake, I will show you some fantastic colors using my special piece of plastic. I didn't select that one, but I just happened to have that one. Transparent piece of plastic. We look at it through two crossed polarizers and you see fantastic colors. Alright, so that comes right after this. You're looking now at the light from my laptop, the screen of my laptop. That light is linearly polarized in this direction. Why that is irrelevant. Irrelevant for this demo. But it is polarized, linearly polarized in this direction. I have here another piece, small piece, which is also a linearly polarizer, which also the direction of polarization is in this direction. That's why you can see through this piece and see my screen. Now if I rotate this 90 degrees, then obviously it's totally black. Because light that is linearly polarized in this direction cannot go through this linear polarizer, because it will only allow light through with this polarized in this direction, or maybe in this direction. So, this linear polarizer now, you can see the light from my screen. This is a half wave plate. So light that will go through that will go through twice 13.9 microns. It's quartz. It's only a half wave plate. There's nothing attached to it. No linear polarizer attached to it at all. It's only a half wave plate. Remember that in the problem with the coin, the light goes through 1/4 wave plate to reach the coin, and then it comes back and it has to go again through 1/4 wave plate. So effectively it goes through half a wave plate. And what happened was that the linearly polarized light was rotated 90 degrees when it came out to me again. And that's why in those situations you couldn't see the coin. So this half wave plate, if I put that between my screen and the linear polarizer, this half wave plate should also be able to rotate the linear light from my screen 90 degrees if I put the half wave plate at an angle of 45 degrees. So the screen is polarized in this direction, the linearly polarizer is polarized in this direction. If, however, if I can rotate the linearly polarized light from the screen by 90 degrees, it will no longer be able to get through this. Are you ready for this? About 45 degrees. Black. So it has rotated now 90 degrees. If I do it 45 degrees like this, again. The 45 degrees is the angle between the linearly polarized light and the optical axis of the half-wave plate. And I discussed that in the solutions. All right, so I have demonstrated now that the half-wave plate can do the same that 2 times 1/4 wave plates can do. Now, I have here a piece of plastic that I used at high school. And plastic is birefringent due to the stresses, the tension, which is inevitable depending upon how it was made. The light that goes through the plastic from behind is linearly polarized, remember, in this direction. The degree of birefringence is different everywhere depending upon the tension. The direction of the optical axis is different everywhere depending upon the tension. The thickness of the effective thickness of the birefringent material is different depending upon the tension. So if now I use a linear polarizer and I look at the light that comes to me from the plastic, it has gone through a whole variety of birefringent parts. In some cases, the red color may have been completely killed because it's rotated by 90 degrees. In some cases, the red may have been rotated 180 degrees or 360 degrees, in which case it will go through. And there's all other possibilities in between. So some parts may look green, other parts may look red, other parts may look blue. And that's the amazing thing if you now look at the plastic through linear polarizers. Look at this. Look at this. Is that incredible? I have 2 linear polarizers next to each other. That's easier, so you have a little bit larger area. So now you understand why you see all these colors. Because, so to speak, it is birefringent material out of control. That means different everywhere. If I rotate the polarizers, of course, then the angle between the local optical axes, which is different at every location, the angle between that optical axis and the linear polarizer changes, and so the colors will also change. Okay, so this was icing on the cake. Look at this. I hope you like this. Have a nice day. Take care. And of course, we will be friends. You can do something similar at home. And if your screen doesn't radiate linearly polarized light, then you can use a linear polarizer behind the piece of plastic and one in front. You can also try to use saran wrap and stress the saran wrap. That makes it also a birefringent material, although not as fantastic as the plastic does. Okay then, there we go.
over and out.